Jacob's back. Welcome back. Congratulations.
Thank you, Jody.
On the wedding. We missed you, and you have a new series for us.
I do. A lot more exciting news in the coming weeks with this 8-part series about the NCEP centers. Within the National Oceanic and Atmospheric Administration, they have the National Centers for Environmental Prediction. There's 8 of these that we're going to be focusing on over the coming weeks. First, I wanted to start off with weather outside of our atmosphere, space weather. The Space Weather Prediction Center, SWPC, they focus on what happens between the sun and the Earth, and that creates our beautiful northern lights displays, but it also has a lot of impacts on infrastructure and communication systems when there are solar storms coming from the sun towards the Earth. So the SWPC forecasters use instruments on the ground and in space, satellites, to watch the sun for threatening features. When these solar storms happen, they have to issue forecasts and communicate with a wide variety of industries across the globe. They issue watches, warnings, and alerts based on these forecasts. So essentially, the SWPC, which is located in Boulder, Colorado, monitors the sun for impactful space weather to our society. With the aurora, that's just really one component of what they do. There's a 3-day forecast that you can find on their website, but essentially you have the magnetic field around our Earth. When you have an ejection of protons and electrons, plasma from the sun, that interacts with our magnetic field, and some of those particles can enter at our poles to create our beautiful northern lights display. But again, we're really focusing on this coronal mass ejection with ground-based observations, telescopes focused on the sun, and magnometers which monitor Earth's magnetic field. There's also satellites up to 1 million miles away in space, some that also monitor the Earth, the weather here on Earth. They monitor those particles released from the sun and X-rays. So to explain why those coronal mass ejections are so important to monitor, I talked with Sean Dahl. He's the service coordinator at the Space Weather Prediction Center, which has about 70 employees. They're staffed 24/7 with at least 1 or 2 forecasters there, but more with big events. So Sean is originally from Williston. He went to high school there, and in 1979 in Williston there was a total solar eclipse, and that is what got him interested in space weather. But here he is explaining these coronal mass ejections.
Coronal mass ejections are really a result of localized intense magnetic fields that are on the surface of the sun. As those magnetic fields become stressed out, they instantly reconnect into something less stressful. Sometimes that'll go ahead and release enormous amounts of energy that will pummel back down to the surface of the sun and release a solar flare. And it also may eject solar material, plasma, energetic particles out into space ahead of it as a coronal mass ejection. So what a coronal mass ejection actually is a piece of the sun flinging out into space, billions of tons of a piece of the sun in the form of that plasma, with its embedded strong localized magnetic field being stretched and pulled out into space along with it.
So even though they do have aurora forecast on their website, they're not really in that aurora forecasting business. It's a lot more about the impacts that these coronal mass ejections have on communications and infrastructure here on Earth.
But what we're really doing is supporting infrastructure and technology, customers that operate those things, whether it's the power grid, which can be dramatically impacted by an extreme space weather event to the point of potential collapse. That's the main federal government concern there. Satellites, operating them properly, whether it's satellite communication or the actual physical infrastructure of the satellite, can be damaged by extreme space weather storms. Astronaut health, aviation can be harmed by radiation exposure due to extreme space weather events of a certain type if they're in the right place at the wrong time, if you will. GPS accuracy, which is important to North Dakota. A lot of the combines and things are using precision GPS to navigate and be within accuracy of inches, right, when they're working on their crops. That can be dramatically off the mark when it comes to an extreme space weather event as well. Our products are trying to get more tailored to individual needs. For example, the power grid, eventually we hope to get to a point where we're not doing a planetary geomagnetic forecast, but we can tailor it to, say, the upper Midwest. The Red River Valley area for the high voltage transmission lines coming out of Canada into North Dakota, and give them a sense of what the actual induced current is on those in amounts of volts per kilometer.
So the Space Weather Prediction Center puts these solar storms on a 5-point scale. You can kind of think of it like the hurricane scale from Category 1 to Category 5, where with a minor solar storm, geomagnetic storm, you can have weak power grid fluctuations, whereas when you get up to a G3 strong geomagnetic storm, that can lead to more impacts to our power grid, satellites, and radio frequency communications, all the way up towards the very rare, severe, and extreme geomagnetic storms. And what the Space Weather Prediction Center is doing, they have to communicate with a lot of different entities to prepare for those level of storms, and they only get a few days in advance notice with when the mass is ejected from the sun to when it impacts Earth's magnetic field. So a couple of recent examples of large solar storms. Last year there was a G4 storm that disrupted precision GPS. So in Canada they had to suspend drilling operations because it couldn't be offset with those GPS communications being compromised. Induced currents on power grids in the northern part of the United States. They took action to mitigate any problems. And more recently in December, air traffic control communications was almost impossible in some cases for about 8 minutes when there was a strong solar storm that impacted Earth. So with the Space Weather Prediction Center, they communicate with the Air Force, their core partner, communicate with them every day for observations and other things. NASA, astronaut health with radiation analysis. The power grid, once they hit that G3 strong level, they need to call with coordinators that are in charge of most of North America's power grid. The Space Weather Prediction Center gives them a heads up. Air traffic controllers are also on their short list of who they need to talk to when these events are happening, and even they can talk with FEMA and the National Security Council if it gets to that level. Right now we're actually increasing solar activity into this next solar cycle, and Sean will explain more on that.
We are currently approaching the maximum of solar cycle 25. That's now predicted to be this year at some point between now and October. We'll see if it has to move on into 2025. But either way, that just means we're at the most risk for the more severe and extreme events, especially in the form of these coronal mass ejections and solar flares and radiation storms. But it doesn't just come to an end and then come down. It takes a few years. So all of this year, all of 2025, and even into 2026, we're going to be at the highest risk during the solar cycle for the more severe and extreme events.
So they'll be pretty busy in the coming months and over the next couple of years with that increased solar activity. And as he mentioned in the previous soundbite there, they're trying to tailor their forecast more to all the different impacts that these solar storms have on Earth with the power grid, GPS communications, and the like. So pretty interesting work that happens at that office in Boulder, Colorado, the Space Weather Prediction Center, and we'll continue this series in the coming weeks with other national centers.
Okay, look forward to it. Thanks, Jacob. Are you here to talk about how great the weather is?
There's a reason behind the great weather.
Yeah?
Okay.
Well,
and
that's
there's a reason why we can forecast that great weather, and it's because of weather forecast models.
I love it.
And someone has to develop those models so that we can predict the future.
Yeah, true.
And that's the jobs of the Environmental Modeling Center. So we're continuing our NCEP series this week, the National Centers for Environmental Prediction within the National Oceanic and Atmospheric Administration. We talked about weather outside of our atmosphere, space weather last week. This week we're talking about the Environmental Modeling Center. So when we show weather forecasts on air, hour by hour forecast, they're derived from these global or regional forecast models that are developed by the Environmental Modeling Center. So for example, their flagship model is the GFS, the Global Forecasting System, and that solves equations of our atmosphere for every couple of hours into the future for several weeks out. And it's used throughout the entire globe. So it's not just that regional zoomed in view over North Dakota that we're oftentimes showing. It's solving these equations for precipitation, cloud cover, humidity, wind speed, etc., all throughout the entire globe on grid spacing. So again, it's developed by the Environmental Modeling Center. They're responsible for the development and implementation of more than 20 of these weather forecast models. They're called numerical weather prediction systems. They transition these systems, once they develop them, into operations for us to use for the National Weather Service, the entire weather enterprise. They're located in College Park, Maryland. So numerical weather prediction uses mathematical models, all these fancy, complicated physics equations, of our systems on Earth. So that's the oceans, how they're coupled with the atmosphere all throughout the different layers, solving those equations based on current conditions, surface observations, radar, temperature, wind speed. Those are fed into the models. We launch weather balloons to get current conditions. We use satellites to get information throughout the entire atmosphere all around the globe in areas where it's not possible to sample atmospheric conditions on the ground or in the air from airplanes or the like. So again, you're putting all of these initial conditions into these numerical weather prediction systems to predict the future in a sense. And it's based on a grid. So you have a specific grid size, and that has gotten smaller over time. That's a good thing because that's better resolution, better spatial resolution that you have these grids. They're only a couple miles from side to side as well as vertically in the atmosphere, because each one of these grid spaces then has to correlate or interact with the nearby grid spaces. So you're solving each one of these equations for the future for each one of these grid spaces. So it's really complicated here, but you're using these models to solve the future of our atmosphere and how that interacts on a global sphere. So there's three branches in the Environmental Modeling Center. The modeling and data assimilation branch, they develop the models, what goes into them, get the best initial state of the atmosphere to plug that in. You have the engineering and implementation branch. They help to get the model into a workflow that hopefully doesn't crash. And then the verification, post-processing, and product generation branch, they fix the models, identify biases that happen with the models, and how to get the most out of those models. So it's a collaborative process, especially between these two branches here, where you're developing the model, you're evaluating it for any issues, the modelers then fix that model and send it back to the evaluators, kind of this back and forth here, where you're improving these forecasts over time. And if it's a big problem, they can perform a crisis fix. Otherwise, they try to combine all these fixes together into a newer model upgrade. So you want to make sure that the model upgrade is better than what you already have. Usually they have to run it through forecasts of the past 3 years just to make sure that it performs well in all of the different seasons and doesn't have too many biases. So we're going to hear from Alicia Bentley here in a second. She's part of the Global Verification Project, part of that model evaluation group, which looks at case studies of high impact weather events, performance compared to similar models. How does the model that they're looking at compared to these other ones, make sure things are lining up? If there's any biases, is it too cold? Is it showing that the storm is moving too fast across the country on a consistent basis? And trying to just document these errors over time. So they use a combination of statistics and case studies. And Alicia will explain why that's important.
For the statistics that we calculate, we do them for all of our operational models. And it's basically to say, what are the known modeling issues? Say in winter, over a certain region, temperatures coming out of a particular model are always too cold. That you could see in an average statistical sense, but then you could also find individual cases, like individual case studies, to prove that point and show forecasters in real time.
So there's a few specific models that I wanted to highlight that they have developed. We looked at the Global Forecasting System, the GFS, at the beginning, but they also have these more regional models that are higher resolution. One is the HRRR, High Resolution Rapid Refresh Model. They also have some other ensemble-based short-range models, so only going out a few hours into the future, and these are really useful for summertime severe thunderstorms and looking at those specific types of weather events on a kind of more high resolution basis instead of having to solve these equations for the entire globe. And one of the biggest advancements that has come from these models in looking into the future is how we capture those initial conditions. And Alicia will kind of talk about that here.
I think one of the biggest things that we've done in the last 25 years is improve the observations of initial conditions. So we're capturing the atmosphere in its current state better. And that's because of the advent of satellites that are, more numerous and help us get data from places that were data sparse before, meaning like we didn't have observations. You can think of that like the middle of a desert, the middle of an ocean.
So you have to take all these initial conditions through a process called data assimilation in order to figure out what's happening in between those observation points in the atmosphere. That's a huge improvement that has happened over the past couple of years. Another huge improvement has been to our supercomputers. This center uses some of the most advanced supercomputers in the world because they need to run, for example, these models 4 times per day, especially the global ones, out into several weeks into the future, as well as develop new models. So you have those models that are being used in day-to-day operations, plus on these supercomputers, you're running models that are in development, and those could have multiple different variations running on that same supercomputer to figure out which one is going to be the best, to then fix that model, iterate it into the future in order to get a better result and more accurate forecast. And there's 2 main supercomputers that they use, one in Phoenix and one in Virginia, because they want to keep these on 2 separate power grids in case something catastrophic were to happen. You would always have one of these supercomputers up and running at all times. Some of the latest research coming out of the Environmental Modeling Center is with a hurricane analysis and forecast system that would track a hurricane on its forecast track, hone in on that and try to figure out exactly where the hurricane will go, look at specific parameters with especially tropical forecasting. The rapid refresh forecast system, that will hopefully combine a lot of our regional models that we have right now, the high resolution things that we're especially using for severe summertime weather, into one kind of ensemble based model. And then the seasonal forecast system, that they hope to use to forecast out to a year for the first time. So looking at that longer time scale. And that's the key with the Environmental Modeling Center. It's a bunch of different models that they're developing and improving over time for a bunch of different time scales to give us the best information. There's so much data out there so that we can, at the end of the day, create the best forecast and then pass that information along to you.
So amazing. I mean, technology has changed, and all the trillions of calculations. The accuracy of the 7-day today was 3 days back in the 80s.
Yeah, isn't that
so I mean, it's
wild?
amazing how you go out in
So
the future.
imagine
and
what
be
it'll be
accurate.
like in another 20 years.
Yeah.
Thank
But
you.
you got to think what's behind those models, what's behind the forecast.
It's all in how it starts.
Right, and the
Yeah.
Environmental Modeling Center, big part of that.
Yeah,
All
thanks,
right.
Jacob.
You're welcome.
Thanks, Jacob.
NCEP, we've been talking about that, National Center for Environmental Prediction, and now one segment of that is the Climate Prediction Center, which we talk about a lot, and that's
Yeah.
what Jacob's going to discuss.
We show a lot of their maps on there. You might not know that a lot of them are made by the Climate Prediction Center. So we're going through the series here under the umbrella of the National Oceanic and Atmospheric Administration, talking first about the center that focuses on long-range outlooks, and then in the coming weeks we'll get into the shorter-range forecasting centers. But climate is what we expect. Weather is what we get, as said by Mark Twain. So there's a distinct difference between weather and climate. Weather is short-term changes in the atmosphere in the minutes, hours, and coming days. Forecasts of specific events in that shorter time scale. Climate describes average weather conditions in a specific area over a long period of time, typically 30 plus years. And that can show us patterns over time. So with the 30 plus years, we use that 30-year average, past 30 years, to come up with our climate normals. And for May, this is what our climatological averages are. So for May 1st, today, 63 degrees normal high temperature. By the end of the month, climatologically, we're typically in the mid-70s. And you can see that for our normal lows and precipitation as well. Again, that's the climate, what we expect for a month. Well, what's the forecast for this month of May? And this is from the Climate Prediction Center, using a bunch of different models and prediction tools to come up with this map. Equal chances. So we'll dive into what that means in a couple of minutes for above or below normal temperatures, and at roughly equal chances of above or below normal precipitation as we go through this month. So you can really expect near normal as we go through this month of May. For a little bit of a shorter range, 6 to 10 days, that's where the Climate Prediction Center starts their outlooks. And we can expect above normal amounts of precipitation and a slight signal towards below normal temperatures. But where you can see this difference between below normal and above normal temperatures, they can really trace out the jet stream pattern across the country. So what do these maps mean? So you see that cooler than normal and warmer than normal on the maps, but in the middle you have that equal chances. That's a third chance of well below normal, a third of a chance of near normal, and a third of a chance of well above normal. If If you go to the cool side of things and it's in that dark blue shading, that's a pretty high confidence in well below normal temperatures. It doesn't dictate the magnitude. It doesn't mean that temperatures will be very below normal. It just means that it'll be below that climatological average for the past 30 years. And the same thing, the higher the confidence that you have on the warmer side, the darker the color will be on that map. So to predict these long-range forecasts, you have to look at teleconnections. There's significant relationships or links between weather phenomena at widely separated locations all around the globe. And you can think of the jet stream as a superhighway carrying weather systems all around the globe. And with the peaks and troughs to the jet stream, that impacts temperature, rainfall, winds, etc. And it all has downstream impacts, like a river, where if there's a dip or a peak in the jet stream over the Pacific Ocean, that will have an impact over North America. And it behaves like a seesaw, these teleconnection patterns, positive or negative phases where the jet stream's in certain positions, that leads to different temperature and precipitation outlooks. And here's a whole list of the teleconnections that we as meteorologists look at, the Climate Prediction Center looks at to make these outlooks. A lot of them are in the Pacific Ocean, and with weather moving west to east, that has pretty big impacts here in the United States. So everything is connected around the globe. El Nino is in the equatorial Pacific Ocean, but that can have impacts on rainfall all across the globe when you look at those jet stream patterns. So multiple teleconnections happen at the same time, and they can override each other, or they can constructively amplify the signal. So there's lots of chaos and noise in the atmosphere all around the globe. So we need to parse out all of that data, and the director of the CPC will kind of explain that here.
I mean, this can be characterized as a small signal, large noise problem. And so you are just getting these shifts in a probability space, and you need to understand that, right? So that if we say it's a 50% probability of being above normal temperature at your location, that means a 50% probability of not being above normal, right? And so you have to look at both sides of that coin.
So you have to look at those probabilities still when you're looking at these maps. There's still a chance that it'll be above normal even though you're in that favoring for below normal. It's all about where the odds are favoring in your specific location. When you look at all of these different signals, the teleconnections are one tool that these forecasters have, but also long-range weather forecast models. They can be pretty powerful when looking at all this data to parse through it to make the outlooks. Other products that the CPC is responsible for are seasonal outlooks. So when you see us talk about the outlook for the upcoming summer, they're a really good guide that we can go off of. They have hazard outlooks for the next 2 weeks, so above or below normal temperatures, excessively high temperatures, or maybe an onset of drought coming, because they also talk about the drought outlook. They partner with the drought monitor and look at even drought information systems across the globe and famine that can happen in certain parts of the globe. So it's really a support network throughout different agencies that they have to communicate with. And they've even looked into ocean monitoring and help with the Hurricane Center outlook each summer. So it's a pretty big breadth that they have to forecast for in that longer range. And then there's other centers that we'll talk about in the coming weeks that focus more on the short range forecasting.
Looking forward to that too.
Okay, thank
so
you.
It's not just looking out the window. There's a lot of data points. that
I
go into it.
never
Yeah.
said that's
All right.
all you did.
But maybe
It's a
you
little
would think that.
defensive.
A lot of different prediction centers under that NCEP umbrella we talk about
Okay.
today. It's about the Weather Prediction Center.
And they're responsible for a lot of different things. Last week we talked about the Climate Prediction Center with those much longer range outlooks in the weeks, months, and even seasons into the future. Weather Prediction Center really focuses on the next 7 days. And they have a lot of different products, but they're co-located with the Climate Prediction Center, a few other NCEP centers at College Park in Maryland. With 30 to 40 forecasters at the Weather Prediction Center, they have two branches, forecast and operations, and development and training. And these are a short list of some of the products that they're responsible for, and we'll go over them here in the next couple of minutes. So first, drawing surface analyses. They do this every 3 hours, where they're drawing cold fronts, warm fronts, stationary fronts, occluded fronts. Cold fronts, you have the cold air coming in behind that front. Warm front, warm air moving in behind the front. Stationary, there is a boundary because of wind shift converging winds, differences in temperature. Occluded front, that's when a system is really late in its life cycle and really well developed and mature. And then you can also have these other symbols on these surface analyses that they draw, squall lines associated with thunderstorms, as well as dry lines and troughs. So these are drawn by hand, and that's where we get our areas of low pressure, high pressure analyzed just based on surface observations. This was the 1 p.m. surface analysis from the WPC. They collaborate with the Ocean Prediction Center and the National Hurricane Center for these, because the fronts don't just stop over land, they continue over the oceans, and with tropical seasons they need to analyze where the hurricanes and tropical cyclones are. But we can translate those into our graphics and plot the surface analysis across the country right now with areas of high pressure, generally calm weather, areas of low pressure, the storminess, and then the fronts associated with them. Right now there's a pretty big outbreak of severe weather across parts of the Ohio River Valley associated with that stationary front and area of low pressure. Then from that current conditions of the surface analysis, they produce short and medium range weather and frontal forecast over the next 3 days. And these are really easy to understand snapshots of the projected weather over the next 3 days with areas of rain and thunderstorms, and then even projecting that into the next 7 days with the fronts and areas of high and low pressure. Next, they forecast precipitation. So they have these QPF forecasts, quantitative precipitation forecasts. They issue these 2 times per day for the next 7 days at various intervals. They can adjust certain areas by hand, and it's a whole blend of models that goes into these QPF forecasts, as explained by Allison, who's a meteorologist at the WPC.
So it's kind of our job to analyze those models, decide which ones we like, and then we have specialized blending tools at WPC that we use to kind of be able to pull in any of those models. We can tweak individual percentages of which models we like.
So it's a bunch of different forecasts that get blended into just this one product that we show on air oftentimes for the next, let's say, 2 days or next 7 days all across the country. And they can adjust those regionally or based on biases with the models or certain trends that happen when certain patterns are in place across the nation. The next product that they're responsible for is the excessive rainfall outlook, or the probability of seeing flash floods. And it serves as a basis for flood watches and flood warnings, which are decided by the NWS offices, the Weather Service offices located all across the country in each region. So for example, today, Nashville, Tennessee is under the gun for this moderate risk of seeing excessive rainfall, and that means a good chance of seeing flash flooding. So this really hones in on that forecast of why does it matter that we're getting a lot of rain in a certain area, and Allison will explain that.
Why does the 3 inches of rainfall that we're forecasting, why does that matter, and what are the impacts of that in terms of what kind of flash flooding are we expecting out of that amount of rainfall, which of course varies no matter where you are in the country based on a number of factors.
So it's a 4-point scale for these excessive rainfall outlooks, from marginal, where there could be some minor areas of flash flooding, but it's not expected to be widespread, all the way up to slight, moderate, and then the rare high risk of flash flooding, where they're expecting widespread flash flooding, and there's going to be possibly some pretty big impacts to travel, services, and possibly some fatalities associated with these flash floods, because the high risk is, again, that highest level category. So in the big picture, these excessive rainfall outlooks orient people for the potential of seeing that excessive rainfall or that flash flood potential. Where is the risk higher? And it describes that probability of seeing rainfall exceeding flash flooding guidance within 25 miles of each forecast point there. And the reason why that high risk is really important to be aware of is because they're only issued on about 4% of days throughout the year, but the high risk days have accounted for 1/3 of all flood related fatalities and 4/5 of all flood related damages. And they're most common, those high risk, high tier days on that excessive rainfall outlook, across the deep south, Gulf Coast, where you see a lot more moisture there. Not really as common as we get into our region here in the northern plains. Then on a much shorter time scale, they issue mesoscale precipitation discussions, and these are for the next couple of hours where they're really honing in on areas of flash flooding risk because of training thunderstorms. Let's say thunderstorms moving over the same area in a constant line. Area of moderate to heavy precipitation is really just staying over the same area, and that'll lead to probably flash flooding that will be imminent. Then with winter storms, this is one of the other desks that they have at the WPC with the Winter Storm Severity Index, combining a bunch of different indices or different variables together to create this more one-look graphic of how impactful will a winter storm be. And finally, you probably see these graphics that we talk about during the winter time, the probability of exceeding a certain amount of snowfall. So all of these different products, they're fine-tuned by the forecasters at the WPC, and we're appreciative of the work that they do, but it's all about the analysis of all the different models and data, and we do that on our end too.
We certainly do. It still takes meteorologists to decipher the just millions of data points, right?
Dumb it down for us.
You got to
guys.
dumb it down.
Please
Weather
do
Prediction
that.
Center does that,
Yeah.
and we help to display that on the air.
The impacts of the forecast.
So true.
All right, thanks, Dave.
All right, this is one of the centers meteorologists use almost on a daily basis, the Storm Prediction Center. It's one of our go-tos, and Jacob, you're going to tell us all about it.
Especially as we're getting into summer severe weather season, we're working through the National Centers for Environmental Prediction, this time talking about the Storm Prediction Center. It's located in Norman, Oklahoma, on the campus of the University of Oklahoma, in the National Weather Center building. They have two branches. The operations branch has 3 to 6 convective thunderstorm forecasters there at a time. So the convective thunderstorms, you get those storms to bubble up in the summertime. It's a convective process, and that can lead to severe weather. They monitor multiple areas of the country and produce national forecasts. They also have a fire weather forecaster on staff at all times because they're responsible for forecasting the spread of large wildfires. And then the other branch is research, techniques, and development. So the ideal scenario with severe weather is you have the Storm Prediction Center issuing outlooks in the days before a severe weather event. The day of the event, they issue mesoscale discussions, which really hone in on areas of thunderstorm development that could turn severe in the coming hours, and maybe hint on issuing a severe thunderstorm or tornado watch in the next couple of hours. And this can get a little technical with the certain parameters that are in place in the current environment. Then the watch gets issued in collaboration with the Storm Prediction Center and the local National Weather Service offices. Then the National Weather Service offices issued those much smaller warnings for the imminent danger of severe thunderstorms or tornadoes. So at the Storm Prediction Center, they take a lot of data from forecast models and draw these outlooks all across the country. Now in the extended range, days 4 through 8, there's a lot more uncertainty, so they're just trying to target patterns that have the potential for a higher end severe weather outbreak. And then in the days 1, 2, and 3 outlooks, they have a 5-category scale, and one of the forecasters at the Storm Prediction Center will kind of explain how they go through this methodology of forecasting severe weather in the days before a possible outbreak.
So in the extended period, much more reliance on the global model guidance, the ensemble guidance. We've turned to using the AI tools that we have in our toolkit now. Those have proven very helpful in the extended period. As we get closer to the near-term severe risk, there's much more of a dependence on the observational data. That's really key here at the Storm Prediction Center, focusing on the observations to ensure that the model data is really capturing the risk correctly.
So today's risk of those severe thunderstorms is really highlighted in the Oklahoma, Kansas, and northern Texas region, where there's a level 3 out of 5 risk for numerous severe thunderstorms. And this risk is based on large damaging hail, severe winds, and tornadoes. And it's all of these probabilities combined. So the risk of a lot of severe storms is really driven by the probability of being high for damaging winds. The tornado probability is not that high in Kansas and Oklahoma, but hail and especially damaging winds are really driving that enhanced risk of severe thunderstorms. And Harry will explain why all these probabilities can be combined into that one outlook map.
So the categories are actually driven by probabilities for each individual severe weather hazard, that being tornadoes, large hail, 1-inch diameter or greater, and severe winds of 58 miles per hour or greater. And that's probability of occurrence within 25 miles of a point. And then those convert to the categories. Inherently, those categories are coverage based due to those probabilities, but they all also have to do with the potential intensity of storms as well, with intensity increasing from that level 1 up to that level 5 risk.
So when we're showing those risk categories on a map, going from level 1, isolated severe thunderstorms possible, all the way up to, let's say, level 3, numerous severe storms possible, to the rare level 4 and 5, where widespread severe storms are possible and likely. So it's coverage based, but also intensity of the severe weather possible. So here's an example from April 27th of this year. They're really good at their jobs because this is the verification of their outlook, and you can see where a lot of reports were of tornadoes and damaging wind and hail right in that bullseye that they predicted of having a severe weather outbreak on that day. And you can really see the evolution of the long-range forecast leading to the forecast in the immediate days before the severe weather outbreak there. So using the longer range to then hone in on the greatest risk area, that's a loop from 8-day forecast all the way down to the forecast the day of a severe weather outbreak earlier this month. So some new things that they're developing is the timing of the greatest threat of the severe storms. So this graph would show, let's say, between 4 and 9 p.m., your severe threat is the greatest in your location. So that's some new information that they're just developing now, as well as using artificial intelligence tools and developing ways to manage all the data that they have to look at to make the forecast. They also have these new conditional intensity forecasts. So there's uncertainty if a storm will develop. But if a storm does develop, that could be a very strong, destructive storm that could maybe produce a long-track tornado or very damaging hail. So communicating that conditional intensity is something new that they're trying to get on board with. The other branch that they really focus on, or the forecast side of things, is with fire weather. You might not think that these two fit together, but there's a lot of similarities between fire weather forecasting and severe thunderstorm forecasting. They both use ingredients-based approaches. Where do these ingredients come together? Where do they overlap in time and space to either support the enhanced severe thunderstorm risk or that fire weather risk? So with the fire weather, critical fire weather days, they're forecasting the potential for large fire ignition and spread with low relative humidity and strong winds to spread those wildfires rapidly. And they also forecast for dry thunderstorms, meaning that there's not rain coming from the thunderstorm cloud, but lightning can spark a fire. So today's fire weather outlook is in that elevated classification in parts of western Texas and southern New Mexico, but you have the elevated, critical, and then extreme level on their scale. Here's an example from a couple years ago where you had very high fire danger in parts of the southern plains, and that was communicated here on this outlook map that they drew. So it's a lot of forecast model data that they have to look at to draw that easy glance map for either fire weather or for severe thunderstorms. And like you mentioned off the top, we use that every day. We communicate that to you on air, whether it's going to be isolated severe storms possible, numerous severe storms possible, or even that rare widespread severe storm threat.
So true. And we, as meteorologists, we can't do it all, right? And the Weather Service here locally issues the warnings, but it's the watch that comes from Norman, Oklahoma. It's all a collaboration. All of the stuff that goes on behind the scenes, it's amazing just to have an accurate forecast. It really is truly amazing.
Well, I'm glad I got you guys watching.
Yeah.
Yes. And
me
that
too.
National Center, the Storm Prediction Center.
It's a great one to tour. I
Yes.
love that tour. I will admit that this is not one of these centers I typically go to, being in North Dakota, but it's a fascinating one at that.
We're kind of far away from the oceans,
Yeah.
but it has big impacts on the entire globe, what happens over the oceans, as well as with the entire shipping industry. So we're working through the National Centers for Environmental Prediction here, now talking about the Ocean Prediction Center. So the OPC, their forecasters continuously monitor weather across the North Atlantic and North Pacific Oceans and issue warnings and forecasts out to 5 days for wind, heavy freezing spray, and other sorts of advisories that are important for ships because the international shipping industry is responsible for the carriage of about 90% of the world trade, and you get all these shipping routes that can be impacted by weather, so it's a vital service that the OPC provides. So they're located in College Park, Maryland. They have forecast desks for the Atlantic Basin, the Pacific Basin, as well as for medium range forecasts. The offshore regional zones are about 200 miles off of the east and west coast of the United States. Beyond that is deemed the high seas, and they also have forecasters for that region. So they collaborate with the National Hurricane Center for the tropical regions, the Weather Prediction Center that we talked about a couple weeks ago, because they forecast weather over land over the United States, and then that weather bleeds into the oceans, of course, and the Hawaii National Weather Service office, located obviously in the middle of the Pacific Ocean there. But the kind of core component that they start with is surface analysis. So this is the current surface analysis across the Atlantic Ocean. Here's the United States. I drew the coastline here. You can see where the fronts are, the areas of low pressure leading to higher winds and rougher seas, and then the coast of Europe on the side there. But Logan at the OPC will kind of explain why these surface analyses are critical.
The backbone of our forecast process is the surface analysis that we actually do 4 times a day on both of the high seas desks. There are not a lot of observations out over the oceans, especially relative to the number of observations that we have over land. So for doing the surface analysis, we're heavily dependent upon satellite data as well as model data.
So to draw these and then issue forecasts, buoys, satellites, those are important. And an interesting thing with satellites is they have this thing called scatterometry, which really indicates where the winds are blowing, what direction, and the speed over the land, with kind of some satellites that are a little bit closer to Earth's surface, polar orbiting satellites. But with the wind and the wave forecast, those are kind of the 2 critical components that they have here. So here's looking over the Pacific Ocean right now with some rougher seas, higher wave heights just off the west coast, because we have a couple areas of low pressure here, and that's churning up the ocean. But watch this area of low pressure east of Japan, kind of in the north central Pacific Ocean. Then here's their forecast 48 hours into the future. That area of low pressure and then leading to higher seas, rougher waters is near Alaska. So that forecast into the future is really important. But the surface analyses serve as a basis for their short-range forecast, specifically with wind and waves. Those are the 2 most critical components.
Our biggest 2 forecast parameters, I would say, are winds and waves. We forecast and analyze what we call significant wave height. A significant wave height of 6 feet might mean that you could see waves up to twice that height. So that sort of information helps mariners know what kind of sea states they might be encountering.
And then to have a whole unified analysis, they have this map here stretching from Asia all across the Pacific Ocean, the United States, and then all across the North Atlantic Ocean. So they also forecast visibility, dense fog, that's important for mariners, as well as lightnings, because thunderstorms can cause winds to be locally higher and be variable in directions. So they also have automated products for wind and waves. Those forecasts are reliant on global forecast models that solve the equations that represent our atmosphere all around the globe. And the forecast products are on their website. They can also broadcast those forecasts over satellites and high-frequency radio directly to ships, which is a way to get those impacts to the end user, to those ships at sea. Now, their core partner, one of them, is with the Coast Guard. So they have briefings each week for impacts off the U.S. East and West Coast for Coast Guard rescue missions. So they can see the actions that are being taken out at sea, because these ships are receiving the forecast from the Ocean Prediction Center and then reacting if there is a rough area of weather and higher seas, rougher waves. Satellites can show where those vessels are and the paths that they're taking, because they're trying to avoid the most hazardous conditions. It's important for these people out at sea to know the conditions well in advance so that they can avoid the area, take action ahead of time. Now, another part of the Ocean Prediction Center is with ice coverage. They have partnered with the U.S. National Ice Center to figure out what the extent of ice cover is over the Arctic and Antarctic. So they use satellites to show that snow and ice cover, plus over the Great Lakes too. So that information helps support the U.S. defense interests, as well as for research vessels in the Arctic specifically. And that snow and ice cover can even be put into forecast models because everything's connected with the ocean up towards the atmosphere. So we might not think about the oceans being that critical to weather here locally, but even if it's not impacting our weather and everything's connected, the shipping industry is huge. Most of the products that we get are on a cargo ship, and they come into a port of entry in the United States, and that cargo ship has to make a trip all across the Atlantic or the Pacific Ocean, and the forecasts from the OPC are really critical to ensure that that ship safely makes it here.
No doubt about it. I mean, it's so cool. I mean, that's a whole that transportation sector is amazing in the oceans.
Yeah.
It really is. So it's a good service to have, obviously. I just learned a lot there too.
There you go.
All
A
right.
lot of information
Thanks
there,
as
so.
always, Jacob.
All right, so we got 2 things going on Saturday, right? Okay, 3. We're going to enjoy the great weather. That's number 1. Number 2, it's the first day of meteorological summer. Number 3, first day of hurricane season.
Getting into that time of
Yeah.
year. Fortunately, we don't have to deal with hurricanes locally, but those impacts are national news headlines when they impact land. And we're going through the National Centers for Environmental Prediction this week, talking about the National Hurricane Center located in Miami, Florida. And NOAA just came out with their hurricane outlook for this year. It's the most aggressive preseason outlook from NOAA ever, with 17 to 25 named storms forecast, 8 to 13 hurricanes, and 4 to 7 major hurricanes, and 85% chance that this hurricane season will be above normal, where the normal for a hurricane season is 14 named storms, 7 hurricanes, and 3 major hurricanes. One of the main reasons is the ocean water in the Atlantic is like bath water. It is very warm. The current water temperatures are at the levels normally found in early August, with 1.5 degrees to 2 degrees above normal across the regions where we see tropical storms develop. Now, it's the opposite case in the equatorial Pacific Ocean, as La Nina is developing with cooler water upwelling off the coast of South America. And that leads to weaker wind shear in the tropical Atlantic Ocean. Wind shear breaks apart hurricanes because it's the change of wind speed and direction with height. So when there's less wind shear and all that fuel for the hurricanes, the warm ocean waters, that will lead to a very active hurricane season. So the NHC will be very busy this year. There's 3 main branches to the National Hurricane Center, from issuing routine hurricane forecasts, marine forecasts, as well as developing new tools and their storm surge unit. So they're responsible for those marine forecasts all throughout the Eastern Pacific Ocean and parts of the Atlantic Ocean and the Caribbean. And their responsibility for hurricanes goes across the entire Atlantic basin, even in the Eastern Pacific, as storms form off the coast of Central America and move towards the west, could impact Hawaii in some cases. And they have to coordinate with international partners, 28 countries across the Caribbean and Central and South America. So Dan Brown at the NHC will go through the process of tracking these storms from initial development to their more mature phases.
Satellite imagery is the bread and butter of our operations. So we're looking at satellite imagery across, the entire Atlantic Ocean, the Eastern Pacific every day. And we're looking for areas of clusters of thunderstorms that could go on to become a tropical storm or hurricane. So we issue a routine, what's called Tropical Weather Outlook. And as those observances begin to organize, that's when we open what we call INVEST on those. And we collect additional information, be able to run model guidance on those systems.
So you go from the INVEST to the tropical depressions, tropical storms, and eventually the hurricanes once they get up to that strength. And then they put out these 5-day forecasts forecasting the track of the hurricane. That cone of uncertainty encompasses 2/3 of the historical error of tracks of hurricanes. It forecasts the center of the storm. So it doesn't include all the impacts, because hurricanes can be hundreds of miles wide. And these are the names that those tropical storms and hurricanes will get this year. We'll start with the name Alberto, and these names are dictated by the World Meteorological Organization. But the Saffir-Simpson hurricane wind speed scale goes from, once it gets to 74 miles per hour, that's a hurricane, Category 1, up to Category 5, the most catastrophic damage with that category hurricane, over 157 mile per hour winds at the center of the storm, right around that eye wall. And the Category 4 hurricanes, the damage scale increases exponentially. So when you double the wind speed of hurricanes, you quadruple the force of the wind, and that just leads to an immense amount of damage from winds as well as with that storm surge. So they also have to coordinate with a bunch of Air Force Reserve hurricane hunters, as well as NOAA, the Aircraft Operations Center, to fly aircraft into storms that might threaten land, with all these different types of missions, from investigative missions to radar missions, flying directly into the center of the storms in order to get better information for forecast models, because when they're flying into these storms, forecasts are generally 15 to 20% better. One of the new products that they're coming out with is storm surge watches and warnings. And Dan Brown will explain more about some of the ways that they're trying to communicate the hazards with hurricanes better.
We now issue a lot more probabilistic products. We issue products that provide what the risk of wind will be, tropical storm, hurricane force. We also issue probabilistic information about storm surge. Storm surge is highly sensitive to both the intensity, size, and exactly where it makes landfall. So running hundreds of realizations to try to understand what your risk is really important for emergency managers to make evacuation decisions.
So a lot of data goes into the forecast to then make those end decisions if you have to evacuate, if you have to take the necessary precautions of the hurricanes coming to your location. So the track forecasting from the National Hurricane Center has greatly improved. The intensity forecasts have also greatly improved, but that's still a bit of a challenge, especially with rapid intensification. When these storms can go from, let's say, Category 2 to Category 4 overnight, when there's an eye-wall replacement cycle or something like that, and that really needs to be able to be pinpointed by forecast models better. But with that track forecasting, the cone of uncertainty has shrunk with increased accuracy. Here's the 2008 cone in blue, and now the current cone is a lot tighter, giving us a more precise forecast of where the hurricane will go. Here's another graph showing us, let's say in 1980, for a 72-hour forecast, the average track error was 360 miles. Now it's only at 75 miles, so much better accuracy of where the hurricanes will go, and that's all attributed to the experts at the National Hurricane Center and all the better observations we have and all the better forecast models that we have to project these storms out into the future. So hurricane season goes from June 1st to November 30th with a peak in early September, but I can bet you that the National Hurricane Center is going to be very busy this year with all the development that's expected because of those factors that I talked about at the beginning.
Fuel for hurricane, you got to have water, right? Yeah. But the temperature is scary here in late May. It's scary, like you mentioned, August temps. Right. It's going to be a busy year.
Yeah. All right. Thanks, Jacob.
You're welcome.
So this past September, I was in Kansas City for the National Weather Association annual meeting. And so my wife and I took a detour on the way to the airport. We had to go to the Aviation Weather Center and do selfies in front of the building. I don't know why.
Did you guys go inside?
No, we didn't have time. I had to catch a flight.
It was all Luana's idea, I'm sure.
Of course it was. Yeah.
Okay. But I will take you inside here, show you the operations of the Aviation Weather Center. This is the last part of my series on the National Centers for Environmental Prediction, focusing on all aspects of weather across the country and the globe. But this week we're going to be talking about the weather and how it impacts flights all across the globe. So the Aviation Weather Center, as Kevin mentioned, is located in Kansas City, Missouri. So aside from a flight delay due to storms, there are a variety of other hazards that could potentially impact your flight. So the Aviation Weather Center forecasts these potentially hazardous weather conditions to help ensure the most accurate and up-to-date weather information is available for pilots. You might have to change routes of planes. You might need to delay a flight in order to make sure that it's not going to go into those hazardous weather conditions. So within the Aviation Weather Center, there's two main branches. The Domestic Operations Branch focuses on the lower 48, forecasting for these 5 main variables. So turbulence, obviously, there's clear air turbulence and convective turbulence with thunderstorms, but that's your bumpiness in the flight that you would encounter. Icing, with different layers of the atmosphere, can deposit water and then freeze onto the plane, and that could be problematic where you have icing conditions. Sealing and visibility, convective, again, related to thunderstorm development, and that could disrupt planes, lead to turbulence. And then traffic flow management, they can put restrictions or alter routes in order to make sure that planes get to their location safely and to ensure the smoothest ride possible. They also have an international operations branch that focuses on other parts of the globe. So first variable with the cloud ceiling and visibility. So your cloud base is the lowest visible part of the clouds versus the cloud ceiling is the distance between the ground and the base of the lowest layer of clouds that blanket more than half the sky. So we really want to focus on that cloud ceiling as well as your visibility distance. And there's different categories here, ranging from LIFR to VFR. So you can have green to red to magenta. Good conditions when there's not many clouds in the region, visibility is great, and very bad conditions when that cloud base is really close to the ground and visibility is low for taking off of flights. Icing, here's one of their forecasts from the Aviation Weather Center's website, identifying those areas across the country that have that icing threat, because icing can be pretty impactful to flights with decreased lift, increased weight, drag, and reduce thrust, and there's different layers of the atmosphere where there's super cooled water droplets in the atmosphere, specifically when you have really tall clouds, can deposit themselves onto planes' wings in clear or rime ice formats. And then with the convective warnings, they're called SIGMETs. It's kind of like a thunderstorm we have here, warning that we have here on the ground, but for airplanes, because those tall cumulonimbus clouds can introduce turbulence and other hazards to planes. And here's that turbulence forecast that they have across the country. And Amanda at the Aviation Weather Center will kind of go more into that turbulence forecast.
So if it is turbulence tied to some sort of thunderstorm or developing storms, that's going to be your convective SIGMET forecaster. And so they're watching radar, they're watching satellite trends, and they're also looking at different model guidance to put out an outlook for where they think there will be the potential for development in the future. As far as when you get your clear air turbulence, they're looking at satellite to watch for certain signatures that are good indicators of turbulence, and then our model guidance as well.
So with the domestic operations branch, you have to forecast the whole lower 48 at the Aviation Weather Center. You get more localized and specific forecasts with the Center Weather Service units. So there's 21 air traffic control centers across the nation. We're mostly within the Minneapolis Air Traffic Control Center. So the CWSUs provide more specific forecasts and advisories for each one of these air traffic route centers. So there's briefings that are conducted by each of these centers every day to provide situational awareness of upcoming aviation issues, as well as forecasts for many of the variables that the Aviation Weather Center focuses on. So there's a collaborative effort there, as well as a few more specific ones here, like surface wind gusts. Today it's very windy, so as planes are taking off and landing, there's extra precautions there that need to be taken so that the flights go smoothly and safety is taken into account. So for example, today, here's that low-level turbulence forecast from the Minneapolis Central Weather Service unit. And then there's even more collaboration with the air traffic control centers, and these match up with the Central Weather Service units. So within the air traffic control airspaces, they're all managed by the FAA Command Center, which is located just outside of DC in Virginia, and Roland will explain kind of the tasks that are done there. On the day that I was talking to him, there were storms moving across the Jacksonville airspace.
We're looking at the storms that are coming across the Jacksonville airspace, and right off the bat this morning, there was a conference to make sure that are we still looking at the same conditions that we saw yesterday for today. So we make adjustments accordingly with the weather information, and then the air traffic folks decide what's the best avenue to keep the air traffic flowing smoothly and efficiently.
So the FAA Command Center focuses on those specific airspaces depending on where the weather is most impactful, and they provide that clear and concise message so that everyone can work together on this plan and then implement the plan. Because there's a lot of moving factors when you look at the aviation space. To get that flight from the starting point to the ending point on time in a safe manner, altering routes based on weather across the nation that could be impactful to planes. So within the Aviation Weather Center, the Central Weather Service units, and the FAA Command Center, it's all working together to make sure behind the scenes that your flight goes smoothly.
There's a lot of coordination and collaboration that goes on,
This
right?
is all your wheelhouse here, weather and airplanes.
I love it all.
Thank you, Jacob.
Yeah, thank